What kind of problem would make you take a perfectly functioning, multi-million-dollar cruise ship and deliberately cut it in half? To an outside observer, this looks like catastrophic damage control, or perhaps the beginning of a scrapping operation. But taking a structure that weighs tens of thousands of tons and cutting it straight down the middle is actually a meticulously calculated growth strategy. In the early 1990s, the United States Navy sliced open the USS Cimarron to insert an additional 108 feet of midsection purely to boost the fleet oiler's fuel-carrying capacity. They completed the procedure under strict military engineering standards and confidently returned the ship to active combat zones. Today, the civilian maritime industry routinely performs this operation. The luxury cruise ship Silver Spirit was cleanly bisected in 2018 to receive a new 15-meter midsection, seamlessly returning to service just weeks later. This radical surgery is known as Jumboization. Operators use a vessel's existing modular architecture to execute massive mid-body insertions, radically improving their financial return on investment and forcing compliance with modern global emission standards. Major operators deploy Jumboization as a high-level capital strategy to adapt aging fleets to modern economic constraints. Building a brand-new vessel from the keel up is an astronomical financial undertaking. Operators routinely face capital expenditures exceeding $500 million. This chart compares capital expenditure against vessel capacity. As you can see, the trajectory for a new build requires massive upfront capital. Conversely, the Jumboization retrofit pathway achieves nearly the exact same capacity increase for a fraction of the cost and time. In the shipping industry, physical deck space directly dictates profit margins. Global logistics giant Maersk applied this exact logic to older Panamax-class cargo ships, rapidly slicing them open to add thousands of new TEU container slots to their aging fleet. But maximizing payload is only half the equation. Today, operators face immense regulatory pressure from two major global emission standards, the Energy Efficiency Design Index and the Energy Efficiency Existing Ship Index. The EEXI mandate legally requires existing ships to carry more cargo while simultaneously lowering their overall carbon footprint. Look at this EEDI equation dashboard to see the hydrodynamic loophole operators use to pass the test. By increasing the cargo volume variable while keeping the main propulsion engines untouched, the ship's overall fuel-to-cargo ratio improves, driving the efficiency score directly into the compliance zone. Because the longer ship now moves far more payload using the exact same amount of engine fuel, this specific mathematical improvement keeps a 20-year-old hull compliant and prevents it from being locked out of international waters. Extending the life of the hull also prevents the need to smelt thousands of tons of steel for a replacement build, slashing the operation's embodied carbon and industrial waste. Strict environmental regulations mathematically incentivize hull splicing as the most resource-efficient method to keep fleets on the water. An operation of this scale requires an immense, highly specialized dry dock to house the vessel before surgery can begin. Before a single torch is lit, engineers manually verify the ship's original blueprints. Because ships undergo countless undocumented modifications during their service lives, the crew must physically walk and map every inch of the hull to prevent miscalculations. Once the dock is drained, the internal gutting begins. Workers strip the cut zone to the bare metal, meticulously severing, capping, and labeling miles of electrical cable, HVAC ducts, and heavy piping along the intended cut line. On the exterior, workers aggressively blast the paint layers off the steel cut line. This critical safety step prevents lethal, toxic fumes from flooding the dock during the thermal bisection. The structural cutting sequence follows a strict mathematical order. Engineers direct the slicing plate by plate and deck by deck to maintain the hull's static structural stability until the last possible moment. Workers deploy semi-automatic track machines to cleanly slice the flat exterior plates, while relying on manual hand torches to navigate the complex curves of the internal skeleton. Once the structural integrity is fully compromised, operators utilize specialized hydraulic skid shoe systems to manage the severed mass. Operating on computer-controlled rails, a single skid shoe can lift and maneuver over 1,000 metric tons of steel with absolute mechanical precision. The physical separation begins. The bow is slowly, incrementally slid forward. Operators stop constantly to check for uncut, snagged lines, before revealing the open air between the bisected hull. The void is then filled by the brand new midsection, built precisely to the original specifications and rigorously tested before rolling into position. Safely dismantling a massive floating structure relies entirely on controlled static mechanics and flawless physical sequencing to prevent a premature collapse. Inserting a new midsection is possible because ships are built using modular naval architecture. Shipyards construct massive vessels in separate blocks from the start, and Jumboization leverages that exact same logic. The cut exposes a raw, incredibly complex internal skeleton that must be perfectly mated to the geometry of the new module. Engineers face a monumental challenge, joining 3 distinct multi-thousand-ton segments of steel with zero margin for error. To solve this alignment problem, surveyors utilize a specialized instrument called a total station. The total station relies on high-precision laser metrology. It bounces beams off reflector targets strategically bolted across the 3 separate hull segments to map their exact orientation in space. This wireframe visualization demonstrates the high-precision laser metrology required to validate the alignment. Engineers check structural deviations and angles until the 3 segments settle within a tolerance of a single millimeter. If the alignment is off by even a fraction of a degree, the resulting final welds will bear uneven, asymmetrical load stress. Once the rigid hull encounters the massive torsional forces of the open ocean, that localized uneven stress creates a catastrophic shear point, threatening to tear the vessel apart. Without precise laser metrology, the structural integrity of the newly welded hull would be compromised by invisible internal physics. Even after the internal nervous system of wires and pipes is reconnected, the newly unified hull cannot immediately take on passengers. It must be treated as a fully experimental, brand new vessel. Engineers subject the ship to aggressive hydrodynamic sea trials. They apply maximum throttle to verify the vessel's top speed and execute violent crash stops to guarantee the added mass hasn't dangerously extended the braking distance. They perform high-speed maneuverability and rudder testing in the open ocean to prove the extended hull can still safely turn. Splicing 15 to 30 meters of steel into a ship permanently alters its center of gravity and its buoyancy baseline. This cross-section diagram demonstrates the inclining experiment required to map that physics shift. By physically tilting the hull 15 degrees, engineers mathematically recalculate the righting arm by measuring the shifting center of buoyancy against the new center of gravity. Lengthening the hull alters how vibration waves travel through the physical structure. Inspectors map the harmonic resonance to verify passenger comfort and confirm the massive propulsion shafts continue to spin in perfect alignment across the extended space. Only when these grueling trials are complete does the fully validated ship return to normal fleet operations, showing no outward signs of its extreme surgery. Jumboization succeeds through existing modular architecture, precise naval metrology, and high ROI macroeconomic logic to delay the scrapping of a perfectly sound hull. Ship stretching represents the ultimate life extension technology, leveraging extreme physics to transform sound existing hulls into modern sustainable assets.